Settle in and let go. There's nowhere you need to be, and nothing you need to hold on to. Slowly, we'll drift into the quiet depths, where one of the ocean's oldest creatures moves. If you find rest here, subscribe, and a new one will be ready each night. In the white chalk of a seabed that no longer exists, pressed into soft mineral sediment beneath a shallow warm sea, there is a tooth. It is small. 3 fine cusps rise from a shared base, each one tapering to a slender point, and between them the ridges curve like the tines of something made for gripping rather than cutting. The chalk that holds it is pale as bone, fine-grained, yielding the compressed remains of countless tiny shells that fell like snow through warm Cretaceous water for millions of years and gathered here, slowly, in the dark beneath the light. This particular stretch of seabed, now exposed as white cliffs along the coasts of England and Belgium, lay at the bottom of a shallow tropical sea approximately 95 million years ago. The sun reached down through that water. Ammonites moved through it in their chambered shells. And somewhere in the depths beyond the sunlit zone, a shark with this exact tooth, these 3 fine cusps, this shared base, this precise trident form, move through the dark water in a body almost unchanged from the one that moves through the deep ocean today. That correspondence is not a coincidence. It is not a gap in the record, or a trick of preservation, or an accident of convergent form. It is a signal. Something about the design of this animal was so well fitted to its world that the world found no reason to revise it. The tooth that a researcher holds between 2 fingers in a university laboratory in Brussels, extracted from Cretaceous chalk and wrapped in archival paper for a century before being studied, matches in almost every measurable dimension the tooth of a frilled shark caught in a commercial trawl net off the coast of Japan last year. 95 million years separate those 2 teeth. The planet has changed beyond recognition in the interval, and the tooth has not. The chalk that preserved this fossil began forming during the Cretaceous period, a long interval of geological time that lasted from roughly 145 million years ago to 66 million years ago, the same period that ended with the mass extinction that killed the non-avian dinosaurs. The sea that deposited that chalk was warm and shallow, full of light near the surface and dark below, the same gradient of illumination that governs every ocean on Earth today. The shark, whose tooth was caught in that sediment, was not a curiosity of that era. It was already old. The elasmobranch lineage, the great group of cartilaginous fishes that includes all sharks, all rays, and all skates, extends back not 95 million years, but something closer to 450 million. The earliest evidence of sharks in the fossil record appears in rocks from the Ordovician period, when the continents were arranged in configurations that would be unrecognizable today, when the land was largely bare rock and the oceans held the only complex animal life. These were not the sharks of any modern picture. They were small, primitive, their fins and skeletons still in the process of arriving at forms we would recognize. But they were already sharks, in the sense that matters, cartilaginous, jawed, built around a body plan that would prove over the vast expanse of time that followed to be one of the most durable in the history of vertebrate life. 450 million years. It is a number that passes through the mind without catching, too large to hold in the way that the body holds temperature, or distance, or weight. To step through it requires patience. The Ordovician ended roughly 443 million years ago, replaced by the Silurian, then the Devonian, the age the fossil record sometimes calls the Age of Fishes, when the seas were dense with jawless forms and armored fish, and the early ancestors of every vertebrate group that would ever walk on land. The first land plants were appearing. The first insects were not yet here. The first land-walking vertebrates were still tens of millions of years in the future, and sharks were already present in the sea, already recognizable in their essential architecture, already fitting the broad outlines of a design that has continued to the present. By the time the Cretaceous chalk was being deposited, by the time the tooth that matches a living frilled shark's tooth was falling into soft sediment at the bottom of a shallow European sea, sharks had already been in the ocean for more than 350 million years. The chalk tooth is not the beginning of this lineage. It is a late entry in a record that begins in deep time, in water that no human lineage, no primate, no mammal, no land-walking vertebrate of any kind had yet come to exist in or disturb. Charles Darwin encountered the puzzle of forms that persist through long geological time without apparent change in the middle years of the 19th century, while assembling the argument that would become his 1859 work on the origin of species. The idea he was building, that all living forms descend with modification from earlier forms, and that the engine of modification is the differential survival of heritable variation, seemed, on its face, to predict continuous change. If the environment shifts, and some variants do better than others, and their traits are passed to offspring, then over time every lineage ought to drift, or branch, or transform, and most do. The fossil record is full of change, of species appearing and disappearing, of body plans arriving and departing across the long intervals of geological time. But Darwin noticed that some lineages did not appear to change, or changed so slowly over such enormous spans of time that the change was effectively invisible in any comparison between the living form and its ancient fossil relatives. He gave these organisms a name. He called them living fossils. He meant the term as a description, not a paradox, simply that these animals or plants carry in their living bodies a form that the rock record associates with ancient time, a form that persisted while the world around it transformed. The term has been debated since. No organism is truly unchanged at the molecular level. Evolution continues in all living lineages, even those whose bodies look ancient. But the morphological reality the term points to is genuine. There are animals alive today whose gross anatomical structure, the shape of their bodies, the architecture of their skeletal elements, the arrangement of their organs, corresponds closely to fossil forms separated from them by tens of millions of years. The frilled shark is among the most compelling of these. Its closest relatives in the fossil record are not merely similar in a general way. They share specific measurable features, the trident tooth form, aspects of the gill arch arrangement, the elongated body plan, that appear in the rock at distances of tens of millions of years without substantial alteration. The body persisted, the blueprint held. The frilled shark belongs to an order called hexantiforms, one of the most ancient surviving branches of the shark family tree. To understand what this means, it helps to hold the shark family tree in mind, not as a ladder, with primitive forms at one end and advanced forms at the other, but as a branching river seen from above. The source is somewhere in the deep Paleozoic, in the Ordovician or Silurian Sea, a single lineage in a warm ocean. From that source branches diverge and divide over hundreds of millions of years, and the branches branch again, and some run dry while others continue. The great carchariniform sharks, the requiem sharks, the hammerheads, the most familiar shapes in the modern ocean, are one set of branches, relatively recent in geological terms. The lamniform sharks, the white shark, The mako, the thresher, are another, and near the base of the tree, close to where the branches first began to diverge from one another, there is a channel that has run deep and slow and relatively unchanged through all the time that the other branches have been splitting and diversifying above it. That channel is the hexenhaciforms. It is not primitive in any sense that implies inadequacy. It is simply early and persistent, one of the first diverging branches to establish itself, and one of the last to be substantially revised. Within the hexenhaciforms, the frilled shark sits in a category of its own. It is the only living member of its family, a family defined by features so distinct from those of any other shark, living or known from the fossil record, that taxonomists have placed it in its own separate family, Chlamydoselacidae, with no surviving relatives close enough to share the category. It is, in the most literal sense, alone in its branch of the tree. To hold a frilled shark tooth beside a fossil tooth from Cretaceous chalk is to hold two moments in time made solid and to feel the distance between them. In one hand, rock, pale, fine-grained, slightly chalky to the touch, the tooth embedded in it or extracted and lying against the white mineral matrix. The three cusps are mineralized, their tips worn slightly by the long pressure of burial, but their form unmistakable, the trident shape, the ridge at the base, the precise geometry of a structure designed to grip rather than slice. In the other hand, a recent tooth ivory white, slightly translucent near the tips, the cusps still sharp. The comparison does not require a specialist to see. The forms correspond. The cusps match in number and in angle. The base ridge corresponds. The overall proportion, three fine points rising from a wide shared foundation, is the same in both. 95 million years between them. The chalk sea is gone. The ammonites are gone. The long warm Cretaceous interval is gone, ending in an impact and an extinction that remade the surface world, and this tooth form remained. The animal that carried it continued to find sufficient food in the deep water, sufficient shelter in the cold, sufficient stability in the conditions below the thermocline, that nothing in its circumstances demanded a new design. The deep ocean, where the frilled shark lives today, has been a place of extraordinary physical consistency for a very long time. Below the thermocline, below the zone where solar heating and seasonal mixing create the variable surface layer, the water settles into conditions of remarkable steadiness. Temperature stabilizes near values that have changed very little across geological intervals. Salinity holds constant. Pressure at depth is immense and unvarying. Light is absent entirely, and has been absent for as long as the ocean has been deep, which is to say for hundreds of millions of years. There are no seasons here. There is no morning and no evening. There is no storm-driven turbulence, no sudden change in chemistry, no shift in conditions between one decade and the next that would not have been recognizable to an organism living here 100 million years ago. This consistency is not incidental to the story of the frilled shark's persistence. It may be central to it. The hypothesis that evolutionary biologists use to explain the phenomenon of morphological stasis, the persistence of body form across deep time without substantial change, is called stabilizing selection. In most environments, conditions shift, climate changes, competitors appear, prey evolve new defenses, or new prey communities replace old ones. Parasites adapt. The physical landscape of the ocean surface changes with temperature and chemistry and sea level. Any organism whose body plan is tightly matched to a specific set of conditions faces pressure when those conditions shift. The variants that fitted the old conditions may no longer do as well and the rare variants that fit the new conditions better begin to accumulate in the population. This is the ordinary engine of evolutionary change, and it runs constantly in the variable, shifting environments near the surface of the world. But in an environment that does not substantially change, an environment that has been cold and dark and pressurized for so long that no geological upheaval has meaningfully disturbed it, the engine runs differently. If the conditions that select for a particular body form remain stable, then the variants that match that form continue to do well, generation after generation, without the disruption that would favor a new design. Selection stabilizes around the existing optimum. The body that works continues to be the body that works. Variation still occurs. It always occurs. But the variants that deviate from the stable optimum do less well, and over time the population remains gathered around a form that the environment has, in effect, continuously ratified. Darkness and cold and pressure, which seem from a surface perspective like hostile conditions, like an environment that demands great adaptation and great biological cost, may be paradoxically the conditions most hospitable to the preservation of ancient form. The deep ocean does not demand change. It does not reward novelty. It holds its temperature and its darkness and its pressure without variation, and the animals that fit it well enough forever. The frilled shark is not the only animal that carries this quality of deep persistence. The coelacanth, a large lobe-finned fish once known only from fossils and thought extinct until living specimens were found in the 20th century, is another member of this loose and informal category. Organisms whose bodies reach back in legible form toward the Paleozoic and Mesozoic record. The horseshoe crab, whose basic body plan appears in Ordovician rock, and whose living descendants still crawl up temperate beaches each spring to breed in the moonlight, is another. The nautilus, moving through the Pacific in its chambered shell, carries an architecture that appears recognizably in Cretaceous rock and in rocks older still. What these organisms share is not merely age, but the specific quality of persistence in a stable environment. The deep sea, the soft seafloor, the tidal flat, the benthic zone, places where the physical conditions have been sufficiently constant across geological time to let a well-fitted form remain fitted across generations beyond counting. The frilled shark belongs in this company. Its body is not a failed design waiting to be improved. It is a design so well matched to the conditions of the deep mesopelagic ocean that the ocean itself has provided no pressure to revise it, and the animal has continued in its cold and pressurized and lightless corridor of the sea as a living record of a body plan that formed before the continents were in their present positions, before the Atlantic Ocean had opened, before the Alps or the Himalayas had risen from the collision of ancient plates. The Cretaceous sea that deposited the chalk where these fossil teeth were found was warm and rich with life. The water near the surface was full of plankton and of the small-shelled creatures whose accumulated remains became the chalk. Mosasaurs moved through the middle water, large marine reptiles with paddle limbs and long jaws. Ammonites drifted in their coiled shells, and below, in the dark beneath the illuminated zone, in water whose temperature and pressure were not so different from the conditions the deep ocean maintains today, something very like a frilled shark moved slowly through the column, waiting in the way that patient animals wait, without urgency, without any measurable awareness of the time that was passing around it, held near motionless in the cold by the ancient physics of oil in water, its three-cusped teeth ready, its body continuous with the darkness. The ammonites above it went extinct, The mosasaurs went extinct. The shallow chalk sea retreated. The seafloor rose and dried and became the white cliffs of Dover, and the continents moved slowly toward their present configuration. And in the deep water, in the cold and dark below all of it, the design continued. The three cusps remained. The body persisted in the form that darkness and cold and pressure had long ago ratified as sufficient, and the animal that carried it continued to move, unhurried, through the deep. In the phylogenetic branching that produced the shark diversity of the modern ocean, the hexant forms diverge from the base of the tree, not with any fanfare of rapid diversification, not with an explosion of forms competing to fill the middle and upper water, but with the quiet persistence of a lineage that found its level early and held it. Other branches diverged and elaborated. The lamniform sharks arrived at the white shark, the mako, the extraordinary filter-feeding basking shark. The carchariniform sharks arrived at hundreds of species distributed across every ocean, every coastal habitat, every temperature zone. The hexanchiforms remained at depth, few in species, unchanged in essential form, occupying a narrow and consistent ecological position that had been available since the Paleozoic and had not been substantially displaced by any of the events that reorganized the surface world above. This is not a story of failure, it is a story of sufficiency. The deep ocean is not a marginal habitat. It is the largest habitat on Earth by volume, a vast cold darkness that covers more of the planet's surface than all the land combined, that has been continuously inhabited by animal life for hundreds of millions of years, and that maintains the physical conditions the frilled shark requires with a steadiness that no shallow or coastal environment could match. The animal did not fail to adapt. It adapted once, deeply and well, to conditions that have not changed enough to demand a second adaptation, and so it remains. There is a particular quality to the image of that Cretaceous tooth, pressed into chalk, surviving the dissolution of the sea that deposited it, the extinction that ended the era in which it formed, the long geological upheaval that lifted the sea floor into air and made it coastline. The chalk is soft, it erodes in rain, the tooth within it is mineralized, harder than the surrounding rock, and it outlasts the matrix that held it. The three cusps that point upward from the pale matrix are the same three cusps that would appear in the mouth of a living animal today, in water so cold and dark that no surface light has ever reached it. The correspondence between those two teeth, separated by 95 million years, by the extinction of the dinosaurs, by the rise of the Himalayas, by the opening and partial closing of ocean basins, by all the vast geological revision of a planet in continuous motion, is one of the quieter facts the natural world offers. It does not announce itself. It sits in a museum drawer in an archival envelope, awaiting comparison. But the comparison, once made, holds something that is not easy to set down. Not astonishment exactly, something steadier than that, something closer to the feeling of standing at the edge of a very long and very quiet duration and understanding that it does not require a witness to continue. The deep ocean holds its cold, the darkness holds its depth. And in the stillness beneath the thermocline, in water that has maintained its temperature within a narrow range for longer than the chalk beds have been dry, the design continues, patient, sufficient, and old beyond any counting that the human mind can comfortably make. The stabilizing force that keeps the frilled shark in correspondence with its fossil ancestors is not a memory or an intention or a drive toward the ancestral form. It is a much simpler thing. The deep ocean remains cold. The deep ocean remains dark. The pressure at 800 feet of depth remains exactly what it was when this lineage was young, because pressure at depth is a function of the mass of water above, and the mass of water above has not substantially changed. An animal that is well suited to these conditions produces offspring that are well suited to these conditions, and they produce offspring in turn, and the variants that drift from the well-fitted form do slightly less well than the variants that hold to it. And over the vast patience of geological time, the form holds. There is no mystery in this, no mystical force of preservation. There is only the quiet arithmetic of selection in a stable environment, the accumulation of small advantages across millions of generations, each generation returning the population gently toward the form that cold and dark and pressure have consistently rewarded. That this process, simple and mechanical and entirely without intention, should produce an animal that carries in its mouth a tooth identical to one formed 95 million years ago in a warm, shallow sea that is now dry chalk in a country far from the nearest ocean, is one of the things about the natural world that arrives slowly and stays. It does not require exaggeration. It requires only patience and a willingness to hold two teeth beside each other and let the distance between them be felt. The chalk was once a sea. The sea is now a cliff. And in the cold water far below the surface of the Atlantic and the Pacific, and the seas off the coasts of Japan and Portugal and New Zealand, a shark with a trident tooth moves through the dark in a body that the deep ocean has found no reason to change, and the darkness holds it, and the cold holds it, and the pressure holds it, gently in a stillness that has persisted, unhurried and sufficient since long before there was anyone to observe it. In the beam of a submersible's light, at a depth where the ocean has been completely dark for longer than any particular creature has been alive, the first thing that becomes visible is the collar. It appears before the body does. 6 pairs of gill slits, each one bordered by a fringe of soft tissue the color of old coral, reddish and pale at the edges, fanning open and closed in a rhythm that is slower than breathing, slower than thought. The first pair of slits does not end where a gill slit on an ordinary shark would end. It continues, crossing the throat of the animal in an unbroken wave of frilled membrane, joining the two sides into a single continuous ruffle that encircles the neck like something ancient and ceremonial. From directly below, in the submersible's cold light, the collar moves. Cold water passes through it, carrying the little oxygen that exists at this depth, and the filaments draw from that water what the animal needs, quietly and without effort, as they have been drawing it since before the genus had a name. The water at this depth holds almost no oxygen compared to what washes through shallower places. A fish adapted to the bright, aerated surface would labor here, but the frilled shark's gill architecture, with its expanded surface area and its continuous first arch, was shaped across long time to work in exactly this environment, in exactly this scarcity, with exactly this degree of efficiency. Nothing about this collar is accidental. Nothing about it is new. The full body comes into view slowly, as the submersible's light widens and the pale form resolves from the surrounding dark. It is longer than it first appears. A frilled shark may reach close to 6.5 feet in a large female, and the body at that length is not a wide, powerful form like the sharks most people carry in their minds. It is narrow and cylindrical, uniform in its proportions from the rounded snout almost all the way to the tail, so consistent in its diameter across such a length that the word serpentine is not a poetic reach, but a simple, accurate description. The body does not taper dramatically at the midsection the way a reef shark's does. It does not swell into the muscular thorax of a pelagic hunter built for speed. It draws out long and even and pale, with the unhurried geometry of something that has never needed to outrun anything, because it has spent its existence waiting rather than chasing, conserving rather than burning. Along the back, set far rearward, almost at the base of the tail, sits the single dorsal fin. It is small. In proportion to the animal's length, it is so reduced that it seems almost vestigial, a remnant of a feature that mattered more in some earlier design, though it still provides some measure of stability in the slow movements the shark makes through its water column. The pectoral fins are reduced as well, short and paddle-like, set close behind the frilled collar, and used not for propulsion, but for minor adjustments of angle and position. They hold the body at a precise tilt in the water, or allow it to change that tilt, but they do not drive it forward with any force. The tail fin arrives last, and it is unlike almost any other shark tail alive. It is not divided into the two distinct lobes that characterize most modern elasmobranchs, the upper and lower arcs, whose asymmetry generates both thrust and lift in fast-swimming species. The frilled shark's caudal fin is a single undivided structure, longer along the upper edge than the lower, without the heterocircle architecture that came to dominate in faster sharks during the long Mesozoic radiation. The tail moves the animal through the water in a motion that is more eel-like than shark-like in the common sense, a slow lateral undulation that begins somewhere near the middle of the body and travels backward in a wave, pushing the water aside rather than cutting through it. The whole form moving the way a ribbon moves in a current, rather than the way an arrow moves through air. It is locomotion built for patience. It is not slow because the animal is weak. It is slow because the animal does not need to be fast, and because every unit of energy spent in movement is a unit not available for growth, gestation, or survival across the long cold gaps between meals. The skin itself carries texture that the light barely catches. Like all elasmobranch, the frilled shark is covered not in scales, but in dermal denticles, small tooth-like structures embedded in the skin and oriented so that they offer reduced resistance in the direction of forward motion, while producing a surface that feels rough to the touch if pressed against the grain. The color in the submersible's light is a uniform gray-brown, slightly paler on the underside, and the tone varies little across the body's length. There are no markings, there is no pattern. The animal is not camouflaged in the elaborate way of shallow water species that need to match the visual complexity of a reef or a sandy floor. At this depth, there is nothing to match, because there is no light to see color or pattern by. The uniformity of the frilled shark's coloration is simply the result of living in a place where pattern offers no advantage, and therefore no particular form of it was selected for across the generations. The eyes are set well forward on the head, large and dark, the pupils expanded to gather what light there is, which at operating depth is almost none. They are functional, useful for detecting bioluminescent flickers in prey or in other animals moving through the column, but in this total environment, the eyes are only one part of a larger sensory system and not the most important part. Running along each flank, from just behind the head to the base of the tail, is a faint groove in the skin. It is easy to overlook in a photograph. It would be easy to overlook in a live specimen seen for the first time, but the lateral line canal that lies within this groove is among the most sensitive pressure detection structures in the vertebrate world. The canal is filled with fluid, and along its inner surface sit clusters of hair cells, each one oriented so that it deflects in response to the microscopic movement of that fluid. When a squid moves through water several feet away, the passage of its body displaces the water around it in a pressure wave too faint for any human instrument to feel. That pressure wave reaches the frilled shark's lateral line, moves the fluid inside the canal, deflects the hair cells, and generates a signal in the nerves that carry information to the brain. The shark does not see the squid. It does not smell it. Not yet. It simply knows that something of roughly that size moved at roughly that speed in roughly that direction a moment ago, and the knowledge comes from the water itself. Read off the disturbance the way a hand reads vibrations in a tabletop, scattered across the head, concentrated around the snout, and along the inner surfaces near the mouth, sit the ampullae of Lorenzini. These are small, gel-filled pores opening through the skin into fluid-filled sacs lined with electroreceptive cells. Every living animal generates a faint electrical field as its muscles contract and its nerves fire. The ampullae of Lorenzini detect these fields at a range of some feet, translating the electrical signature of a living body in motion into information the shark can use. The two systems, the lateral line reading pressure, the ampullae reading electricity, work together, overlapping in their information, each filling gaps the other cannot fully cover. In the darkness of the mesopelagic zone, where no light penetrates, and where the distances between animals are often measured in tens of meters of open water, these two systems together constitute a picture of the surrounding environment that is as detailed as any visual field, simply built from different physical signals. The head itself, seen from the side, slopes gently from the snout downward toward the underside of the jaw. The mouth sits at the very front of the head, rather than on the underside, as in many modern shark groups, a terminal position that places the jaws where they can be presented to prey, encountered at the same depth level, which is where ambush predation in a water column most often occurs. But it is not the position of the mouth that draws the eye once it opens, it is the teeth. Each tooth in the frilled shark's mouth bears 3 cusps. They rise from a shared base in a tight cluster, slender and needle-fine, translucent at their tips if the light is right, curved gently inward so that their points angle back toward the throat rather than forward toward the prey. At the base, a transverse ridge connects the 3 cusps into a single unit, giving each tooth a structure that, viewed closely, resembles a 3-pronged crown or a delicate trident set in pale mineral material. There are roughly 300 of these teeth arranged in rows across the upper and lower jaws, and each one is in some stage of development or active use, because sharks replace their teeth continuously across their lives, older rows moving forward as newer ones form behind them. The front rows are the sharpest and the most active. The rear rows are in various stages of formation, moving gradually toward the front across weeks and months. The mouth of the frilled shark is a structure in constant, slow renewal. A single tooth, removed and held to light, would be immediately recognizable to anyone who had also held a frilled shark tooth recovered from chalk formations deposited during the age of the dinosaurs. The correspondence is almost exact. The 3 cusps rise at the same angle. The transverse ridge sits at the same position along the base. The proportions of the whole structure, cusp length to base width, the slight inward curve of the points, the texture of the enameloid surface, these are the same in the living tooth and in the fossil, across a gulf of time, so wide that human cognition cannot really enter it and feel it fully. The best that can be done is to hold both objects in one sentence and say that they match, and to let that matching carry the weight that the actual duration cannot. These teeth are not designed for cutting. A white shark or a tiger shark uses teeth that function like blades, serrated and wide, capable of slicing through flesh and bone. The frilled shark's teeth grip The three inward angled cusps are arranged so that once they make contact with a soft-bodied prey animal, a squid, most often, or a deep-sea fish, the prey cannot pull backward off the hooks. Any movement backward presses the prey further onto the points. The teeth are a retention system, not a processing system. They hold whatever enters the mouth, and the mouth handles the rest. The jaw is capable of movements that wider-bodied sharks cannot easily replicate. The upper jaw can swing forward and downward, away from the brain case, projecting outward in the instant of a strike, widening the gape to a degree that seems, at first glance, disproportionate to the animal's slender head. A frilled shark can open its mouth wide enough to engulf prey items of considerable size. The protrusible jaw, combined with the highly flexible vertebral column that allows the animal to coil its body before a strike, and combined with the inward-facing teeth that prevent backward escape, creates a prey capture system of considerable effectiveness, one that requires very little movement from the animal during the approach, very little energy expenditure during the wait, and then a single rapid event that resolves the long patience into a meal. But that resolution, the strike itself, and the hunting that precedes it, belongs to a different set of considerations than the architecture of the body that makes it possible. For now, what the light reveals is simply the structure, the jaw that can reach forward, the teeth that do not let go, the gape that opens wider than the narrow head would suggest. The vertebral column that runs from behind the head to the base of the tail contains more individual vertebral elements than almost any other shark species known. This is connected to the elongation of the body. More length requires more segments, more articulation, more flexibility at each joint, and it produces an animal whose spine can bend through angles that a more compactly built shark cannot achieve. The body coils, the body holds a coil, and then, from the coil, the body can extend with a speed that the lazy, undulating locomotion of normal movement does not predict. The column is one of the oldest structural features in the vertebrate body plan, a segmented rod of cartilaginous material that transmits force from tail to head and allows the coordinated muscular wave that is the basis of all fish movement, refined here across a lineage so long that it stretches back before the continents were arranged in their current positions. The skeleton throughout is cartilaginous. There is no bone in the frilled shark, as there is no bone in any elasmo branch. Cartilage is lighter than bone by a significant margin, and in an animal that must maintain neutral buoyancy at depth without a gas-filled swim bladder, a lighter structural material is a meaningful advantage. The cartilage is reinforced with calcium salts in certain high-stress regions, particularly in the jaw, where the forces of a strike require more rigidity than soft cartilage alone would provide. But across most of the skeleton, the material remains flexible and relatively light. This flexibility is part of what makes the coiling motion of the body possible. A bony spine would not bend in the same way. A bony spine would hold a straighter path. And then there is the liver. In proportion to the rest of the body, the liver of a frilled shark is large. It occupies a substantial portion of the body cavity, a pale, dense organ packed with a lipid called squalene, which is also found in smaller quantities in the livers of other deep-sea sharks, and in a few other organisms, but which the frilled shark relies on in quantities sufficient to determine the animal's relationship with the surrounding water. Squalene is less dense than seawater. A liver filled primarily with squalene is a liver that floats, and a body with a liver large enough and oil-rich enough can achieve near-neutral buoyancy in the surrounding medium without any active muscular contribution at all. The alternative would be constant swimming. Many bony fishes maintain neutral buoyancy through a gas-filled swim bladder, an internal sac of compressed air whose volume can be adjusted to match the pressure at different depths, allowing the fish to hover without effort. Cartilaginous fishes have no swim bladder, and those that hunt at the surface, great whites, makos, hammerheads, must maintain buoyancy through constant forward motion, their pectoral fins generating lift as long as the animal moves. Stop moving, and they sink. This is not a problem for animals that hunt by active pursuit and need to move continuously anyway, but it would be a significant problem for an animal that has built its entire feeding strategy around remaining completely still for hours or days at a time in the water column, holding a position while it waits for prey to come close enough to take. The squalene liver solves this in one step. It brings the animal's average density close enough to the density of the surrounding water that the shark can hang motionless in the column, with no fins moving, no muscular expenditure directed at vertical position, no continuous swimming required. The oil does not change volume with pressure the way a gas-filled bladder would, which means that the buoyancy it provides is stable across the range of depths the shark inhabits, without the risk of a gas bubble expanding dangerously during ascent or compressing painfully during descent. The solution is old and chemical rather than new and mechanical, and it works with the same quiet completeness in a living animal today as it would have worked in the same design 5 million years ago, or 50 million, or longer. At depth, in the cold, in the dark, the frilled shark hangs. The liver holds it there, not with effort, not with motion, simply with chemistry, the low-density oil filling the organ displacing water. It is lighter than the water's resistance, holding the body at the right level in the column. The fins are still. The tail makes no wave. The lateral line reads whatever the water carries through it, and the ampullae of Lorenzini sample the electrical field of the surrounding ocean in every direction, and the eyes are open in the dark, and the collar fans slowly at the throat, drawing oxygen from water that offers very little, and the animal is present, wholly and completely, without doing anything that looks from the outside like presence. This is the basic condition of the frilled shark's existence. Not the strike, not the pursuit, not the event, but the long interval before and after, the floating stillness that costs nothing and accomplishes something that is harder than it sounds, remaining alive, at depth in the cold, across time, in a body whose fundamental design has been adequate to this task for longer than the word ancient can honestly convey. The reddish filaments of the collar move again in the slow current. The pale cylinder of the body turns slightly, 1 degree too, as the lateral line registers something in the water some distance away. The liver holds the whole arrangement in place without being asked. The squalene within it, a molecule built from 6 isoprene units linked in a particular chain, has been doing this work, this particular, specific chemical work of keeping a shark aloft in cold, deep water across a time span that includes the rise and fall of entire animal groups, the opening and closing of ocean basins, the accumulation and dissolution of ice ages, and the eventual appearance of a species that would eventually learn to send lights down into this darkness and find hanging there in the beam this animal, this form, this body that has not changed because it has not needed to. The collar opens, the water moves through it, the collar closes, slowly as it has always closed, in water that was cold and dark and present long before any eye existed to perceive it. The shark remains where it is, suspended between the seafloor and the surface, held there by oil, surrounded by silence, entirely at rest in a body that is, in every meaningful structural sense, a record of what worked, nothing more and nothing less than that. The liver does not know what it holds. The The squalene does not know what it is. The shark does not understand its own antiquity. And yet the whole arrangement floats, quietly, in the dark water, as complete and self-sufficient as a stone resting on a riverbed, settled, still, held in place by forces older than the stone itself, requiring nothing from the moment except that it continue. At 600 meters below the surface of the ocean, the pressure is roughly 60 times what it is in the open air above, 60 atmospheres. The weight of that water column does not announce itself with drama or spectacle. It simply is a steady total mineral compression that has no direction, no source, no edge, pressing equally on every surface it contacts, on rock and sediment, and the cartilage of anything living there, indifferent and absolute. The temperature at this depth, in most of the places where the frilled shark has been found, rests near 10 degrees Celsius, not the cold of a winter morning, which the body can brace against and move away from. A permanent cold, built into the chemistry of the water itself, maintained without variation across seasons, across centuries, across epochs. There is no light here, not dim light, not the faint blue of shallow dusk, nothing. The last traces of sunlight, even on the brightest equatorial afternoon, are entirely gone by 300 meters. At 600, the darkness has been absolute and unbroken since the water first settled to this depth. This is the world the frilled shark calls home. Not an extreme environment in the way the phrase is usually used, with its implication of something barely survivable, something at the edge of what life can tolerate. For this animal, these conditions are ordinary. They are the stable center of its existence. The cold, the pressure, the dark, these are not hardships, they are home. The descent begins in the shallows. At the surface, the ocean is a place of constant change. Temperature shifts hour by hour with the angle of the sun. Storms drive water in great circular masses. The seasons turn the chemistry of the upper zone through cycles of warmth and cold, abundance and scarcity, that the organisms living there have evolved in precise calibration to track down. Through the first 100 meters, light still reaches in a diffuse blue-green that dissolves slowly. Photosynthesis is still possible here. Plants in the loose sense, phytoplankton and algae, and drifting microorganisms still capture sunlight and fix carbon and release oxygen into water that still feels, faintly, like the surface it is connected to. Below 100 meters, the light begins to lose its authority. By 200, it is a faint and unreliable presence. By 300, it is gone. This transition, the passage from the lit world to the dark one, is not a sharp line. It is a gradient, a long, slow dimming, and in the zone where it happens, where enough light filters down to be detected by a sensitive eye, but not enough to support photosynthesis, a whole community of life hangs in permanent biological twilight. Lanternfish rise toward the surface at night, trailing their own faint bioluminescence. Squid drift through the middle depths, their chromatophores cycling color through patterns that have no audience except each other. This zone, from roughly 200 to 1,000 meters, is the mesopelagic, the mid-water, the place between the world above and the abyss below. It is here, in the colder and darker reaches of this zone, that the frilled shark most often moves. The mesopelagic is not a single environment. It is a gradient with structure. Near its upper edge, where some light still reaches and temperatures are still relatively variable, the biological density is high, prey is abundant, small fish and crustaceans and gelatinous organisms aggregate in the dim water, rising and falling through the day, in what oceanographers describe as the deep scattering layer, a zone of biological density so thick it appears on sonar equipment as a false bottom, a shadow that rises at dusk and sinks at dawn with a regularity that early researchers found deeply puzzling. Below that upper zone, descending toward the boundary between the mesopelagic and the bathypelagic, at around 1,000 meters, the water cools, the pressure builds, the darkness becomes total, and life becomes sparser, more dispersed, more adapted to the specific economy of the deep. The frilled shark occupies the lower mesopelagic and the transition into the bathypelagic most consistently, though its depth range has been documented from around 500 meters down to at least 1,000, and possibly deeper in some populations. The species does not confine itself to a single depth. It moves within its range as conditions and prey dictate. Though the movements are slow, calibrated, unhurried, the movements of an animal whose metabolism runs at the pace the cold water sets for it, a pace far slower than anything living in the sun-warmed surface above. The continental slope is its preferred architecture, not the open ocean where the water column extends downward into an abyss with no nearby wall, no structural feature to orient against, no concentrated food source. The frilled shark gravitates toward the edges, toward the places where the seafloor rises and the continental shelf drops away into deep water, where the geometry of the ocean floor creates complexity, and where that complexity generates biological richness. Submarine canyons are particularly important. These are vast channels cut into the continental slope by ancient river systems and deepened over millions of years by turbidity currents, dense flows of sediment-laden water that pour down the slope like underwater landslides, carving the rock and sediment of the seafloor into topography as varied and dramatic as any mountain landscape seen from above. In a bathymetric map, a chart that renders the seafloor in the same way a topographic map renders land, the continental margin looks nothing like the featureless slope it is often imagined to be. The shelf edge drops in places near vertically, canyons branch and converge. Ridges run along the slope at various depths, their crests and walls providing hard substrate where sediment cannot settle and where current-swept rock supports dense communities of filter feeders, corals, sponges, crinoids that anchor themselves to the stone and extend their feeding structures into the passing water. Between the ridges and the canyons, in the sediment-filled basins, and on the gentler sections of slope, the bottom softens into the pale mud that accumulates in these depths at a rate measurable in millimeters per 1,000 years, each millimeter a compressed archive of everything that sank from the water above during the centuries it represents. The frilled shark moves through this landscape in darkness, along a canyon wall at 800 meters. The only light that has ever reached this surface is the cold blue glow of bioluminescent organisms, brief flashes, chemical signals, the faint steady pulse of a passing lanternfish, or the startled flash of a disturbed squid. Against the rock face, where the current runs steadily upslope, carrying cold, nutrient-rich water from the deep toward the shallower communities above, the frilled shark drifts. Its pale, elongated body absorbs no light because there is none to absorb. It exists here in a form of pure physicality, pressure, temperature, the faint chemical signals of the water, the electrical traces left in the surrounding medium by the muscle contractions of every living thing within range of its sensory organs. The continental slopes where frilled sharks have been found span an extraordinary geographic range, though the encounters are always rare and always incidental. Off the southwestern coast of Ireland, where the Porcupine Bank slopes into deep water, Trawl surveys have recovered specimens in the cold Atlantic water that sits below the thermocline throughout the year. Off Norway, along the edge of the continental shelf, where the seafloor drops from the shelf into the Norwegian Sea, the same cold, stable water column supports the conditions the species requires. In the eastern Atlantic, the islands of the Azores rise from a vast submarine plateau where the ocean floor sits at depths of several thousand meters in most directions. And along the steep underwater slopes of these volcanic islands, frilled sharks have been documented at depths consistent with their preferred range. The North American Atlantic margin, from New England southward, offers similar habitat, deep, cold, structurally complex continental slope habitat, where deep-sea trawls have occasionally brought frilled sharks to the surface as bycatch, caught alongside the grenadiers and rat-tails and deep-sea skates that inhabit the same depths. In the Pacific, Suruga Bay in Japan occupies a particular place in the record of this species. The bay is relatively small at the surface, an inlet on the southeastern coast of Honshu, bordered by the foothills that rise toward Mount Fuji in the north. Its surface waters used for fishing, in transit, and recreation in the ordinary way of a coastal bay. But the seafloor of Suruga Bay drops sharply and quickly from the shore, plunging into a deep underwater trough that reaches more than 2,000 meters at its deepest point. The cold water that fills this trough is isolated from the main Pacific basin by a shallow sill at the bay's mouth, creating a stable, cold, enclosed deep water environment that supports a community of deep-sea organisms unusually accessible to study by local researchers. It is partly for this reason that some of the earliest and most detailed records of the frilled shark come from Japanese waters. Fishermen working in Suruga Bay occasionally brought specimens to port, and the proximity of research institutions to this accessible deep-sea environment allowed scientists to study living or freshly caught individuals more often than in most other parts of the species' range. In the southern hemisphere, the waters off southern Australia and New Zealand have yielded frilled shark records, and the separate species, Chlamydosylacus africana, occupies the deep shelf and slope waters off the coasts of Namibia and South Africa, where the cold Benguela current upwells along the western African margin and creates conditions of cold, nutrient-rich water that support a different but structurally similar deep-sea community. The two species share their fundamental biology, but occupy separate and apparently non-overlapping distributions, divided by the geography of the Atlantic and the specific thermal and depth characteristics of their respective ranges. This geographic spread is wide, but the encounters are always few, always separated by long stretches of time and vast volumes of ocean. The frilled shark's global range, read as a connected whole, makes the animal seem more common than it is. The inhabited volume of deep continental slope habitat across the planet is enormous, and the frilled shark occupies a small fraction of it at any given time, thinly distributed, invisible to any method of observation that does not reach to the depth it inhabits. The vast majority of documented specimens have come not from targeted scientific surveys using submersibles or remotely operated vehicles, but from commercial deep-sea trawl fisheries, nets dragged along the seafloor or through the mid-water column at depth, designed to catch grenadiers, deep-water hake, orange roughy, and other commercially valuable deep-sea species, and occasionally bringing frilled sharks to the surface as incidental catch. These specimens are rarely reported in systematic ways. Some are discarded at sea. Some are photographed and then returned or disposed of. Some reach port and are noticed by observers or scientists and recorded. The record that exists is the record of these accidents, not the record of the animal's actual distribution and abundance. What directed surveys have occasionally shown comes from remotely operated vehicles, unmanned submersibles equipped with cameras, lights, and manipulator arms, controlled from a surface ship through a tether of cable and fiber optic. When an ROV descends to 600 or 700 meters along a continental slope, its lights cut through the darkness in a narrow cone, illuminating a few meters of rock or sediment, or open water at a time. The rest of the ocean remains invisible. A frilled shark, 2 meters outside the light cone, would not register on any camera. It might register on sonar if the vehicle were equipped with the appropriate sensors, and if the sonar returns were being interpreted with the right expectations. More often, it would simply not be detected. The ocean at these depths is not well surveyed. The territory that has been directly observed by human-operated or remotely operated vehicles represents an almost vanishingly small fraction of the total deep seafloor. What ROV surveys have shown, in the few cases where frilled sharks have been directly observed rather than caught, is an animal that appears calm and unhurried in the presence of an artificial light source, not fleeing, not reacting with the urgency a surface fish might show when suddenly illuminated, but drifting slowly, oriented along the current, moving in the long, slow undulations of a body that has no reason to rush. The water itself, at the depths the frilled shark inhabits, has a chemistry that remains extraordinary in its stability. The subthermocline layer, the cold, dense water that sits below the depth at which temperature drops sharply from the warm surface layer to the cold deep, is one of the most physically consistent environments on the planet's surface. Temperature in this layer, in the North Atlantic and North Pacific, varies by only a few degrees across the full sweep of the year. No storm penetrates here. No seasonal cycle of surface warming and cooling reaches these depths with enough force to shift the temperature by more than a fraction of a degree. The salinity stays near 34 to 35 parts per thousand, with similar constancy. These are not the conditions of an extreme environment. They are the conditions of an exceptionally stable one, a stratum of the ocean that has maintained its physical character continuously and without significant interruption for a span of time that reaches back well before the first frilled shark tooth was pressed into Cretaceous chalk. In that stability lies something worth holding in the mind for a moment. The thermal and chemical consistency of the deep ocean is not merely a feature of the present water. It is the consequence of ocean circulation patterns that have operated in their broad outlines for millions of years. Cold, dense water formed at high latitudes around Antarctica in the North Atlantic sinks to the deep ocean floor and spreads slowly outward through the abyssal basins of the world. A circulation so vast and so slow that water entering the deep Atlantic near Greenland may not reach the deep Pacific for more than 1,000 years. This global overturning circulation, the slow breathing of the ocean's thermohaline system, maintains the cold of the deep ocean and renews its oxygen content and shapes the environment that has sheltered deep sea life across the long stretches of geological time in which that life has evolved. The frilled shark did not adapt to this environment as a new niche. It grew into it slowly, across millions of years, and the environment changed so little around it that the animal itself changed almost as little in return. The subthermocline layer at 600 meters does not experience the seasons. Spring means nothing here. The long days of summer above, when sunlight drives enormous blooms of phytoplankton across the surface and the upper ocean hums with biological activity. None of this penetrates to the depth of the frilled shark's world in any direct physical way. What does arrive, eventually, is the snow, marine snow, the slow drift of organic particles from the surface world downward through the water column, a perpetual soft fall of dead organisms, fecal pellets, shed exoskeletons, mucus, the compressed debris of everything that lived and died in the water above. At the surface, a bloom of phytoplankton produces a wave of organic material that begins its descent within days of the bloom's peak. By the time these particles have fallen through 500 or 600 meters of water, they have been processed and reprocessed by the organisms of the midwater zone, bacteria, protists, zooplankton, small fish, so that only the most refractory fractions remain. What arrives at depth is sparse and chemically impoverished compared to what fell from above. This is part of why the deep ocean is sparse in large animals. The energy that reaches it from the surface has been extracted, digested, repackaged, and partially consumed so many times on its descent that relatively little remains. Large predators at depth must cover large areas, move slowly to conserve energy, tolerate long intervals between successful hunts, and extract the maximum possible nutrition from what they catch. The frilled shark's biology is precisely calibrated to this economy. Its low metabolic rate on its oil-filled buoyancy organ, its slow digestion, all of these fit together with the sparse energy budget of the deep continental slope in a coherence that speaks not to design, but to the slow, patient filtering of variation across millions of generations in a stable environment that rewarded exactly these traits and quietly ended the lines that tried something else. Along the face of a submarine canyon wall, something else happens that brings life to the deep in concentrated form. Upwelling currents driven by the interaction between the prevailing flow of water along the slope and the topographic obstacle of the canyon rim draw cold, nutrient-rich water from greater depths toward shallower ones. As this water rises, carrying with it the dissolved nutrients that have been raining down from above for centuries, the nitrogen, the phosphorus, the iron, it enters the zone where light still penetrates and fuels dense biological production. Phytoplankton bloom at the canyon head. Zooplankton aggregate to feed on them. Small fish aggregate to feed on the zooplankton. Squid follow the fish. And along the canyon wall, where the upwelling water creates a persistent column of dense mesopelagic life, extending from the productive shallows down into the dark, a predator that hunts by detecting electrical fields and pressure waves in total darkness finds something valuable: concentration, a convergence of prey in a structured space. A canyon wall is not just a physical barrier. In the ecology of the deep, it is a kind of infrastructure, a feature that gathers life along its length, the way a reef gathers life in shallow water, through the interaction of topography and current and chemistry. The frilled shark, encountered in waters near Saruga Bay, or along the Atlantic slope, or at the edge of the Porcupine Bank, is always near this kind of structural feature. Not in the open abyss, where the water column descends without interruption for miles, and where prey is distributed at its thinnest, along the edges, along the walls, in the current-swept notches and ridges, where the geometry of the seafloor accelerates the upwelling of nutrients and concentrates the animals that depend on them. The surface of Saruga Bay, on a gray morning in autumn, does not look like the entrance to another world. The water is ordinary, green-gray, textured by a moderate swell, carrying the smell of salt and the faint petroleum trace of boat traffic. The coast road is audible from the water in calm conditions. Fishing vessels work the outer bay. If there is anything remarkable about the surface of this water, it is not visible. The temperature gradient that separates the surface from the deep, begins a few tens of meters below the keel of any boat crossing the bay. Below that gradient, the temperature drops quickly through a narrow depth band and then stabilizes, cold and constant, all the way to the floor of the trough. The deep water of Saruga Bay is isolated enough from the Pacific Basin beyond the bay's mouth that it maintains its own distinct thermal character, colder and more stable than the Pacific at comparable depths, a pocket of the deep ocean's ancient conditions enclosed within a relatively small geographic area. 800 meters below the surface of that gray morning, in water near 10 degrees Celsius, and under a pressure that would compress a sealed airspace to a small fraction of its surface volume, in total and unvarying darkness, the frilled shark exists. Not sleeping in any sense the surface world would recognize, not resting in the way a mammal rests, with a clearly different physiological state of reduced consciousness, simply existing at the pace the cold dictates, with its sensory organs registering the chemistry and electrical content and pressure fluctuations of the surrounding water, its body oriented slightly into the current, its large liver, pale, dense, filled with the low-density lipid that holds it at neutral buoyancy without any muscular effort, keeping it suspended in the water column with no more apparent effort than a cork floating in still water. Between that animal and the surface, 800 meters above it, the entire world of sunlight and weather and human activity continues without interruption, without any knowledge of what persists below it. Ships cross the water, fishing nets are set and retrieved. The morning light shifts from gray to pale yellow as the cloud cover thins toward noon. None of it matters. At 800 meters, none of it reaches. The frilled shark's world and the surface world occupy the same ocean, the same planet, the same moment in time, and they are separated by 800 meters of water as completely as if they existed in different dimensions of experience. This is perhaps the most quietly extraordinary thing about the deep sea. As a place, not the pressure, not the cold, not the darkness taken individually, but the combination of all three working together to create an environment of such physical constancy that the boundary between 800 meters and the surface might as well be a boundary between geological eras. The surface ocean is a place of the present, responsive to this year's weather and this season's temperature and this decade's changing chemistry. The deep ocean, below the thermocline, is something older. It carries the accumulated chemistry of centuries of descent from above. Its physical character has been set not by recent events, but by the broad, slow patterns of planetary circulation that have been running, in their essential form, for millions of years. The frilled shark is at home in both the depth and the oldness. The stability of the deep ocean is not just a habitat description for this animal. It is, in a very real sense, the reason the animal still exists in the form it does. The reason that a creature bearing a body plan and a tooth architecture, recognizable in fossils from the age of the dinosaurs, is still moving through cold water along continental slopes at the edge of the 21st century's ocean. The cold slows change. The pressure is indifferent to morphological variation. The darkness removes the need for the elaborate visual communication and color-dependent camouflage that drive rapid surface evolution. The stability asks nothing new. And in an environment that asks nothing new, an ancient form can persist simply by continuing to work, simply by continuing to move, slowly, along the canyon wall, in water that has been this temperature and this dark since before there were eyes to notice. The wide and discontinuous range of the species, from Irish shelf waters to Saruga Bay to the deep canyons off southern Australia, from the cold Benguela upwelling off Namibia to the deep slope habitat of the eastern seaboard of North America is the trace of a distribution shaped not by recent dispersal, but by the ancient geography of deep continental slope habitat. The deep water that connects these locations is cold and dark and chemically consistent wherever it sits below the thermocline. What looks like a widely scattered set of isolated populations from the surface may be more accurately understood as a continuous habitat that happens to be invisible to most of the methods by which human beings observe the ocean. The frilled shark is not rare in the way a species reduced to a small remnant population is rare. It is rare in the sense of seldom seen, occupying a vast, accessible in principle, inaccessible in practice environment, distributed thinly across hundreds of millions of acres of cold, dark, deep-sea habitat, present wherever the continental slope drops into the subthermocline cold, and the canyon walls provide the structural complexity that concentrates prey. The rarity of observation is a rarity of method, not of animal. A net that reaches the deep rarely targets the frilled shark's preferred habitat. An ROV that descends for a few hours along a small section of slope illuminates a tiny fraction of the canyon wall the animal might occupy. The ocean at these depths is not well enough known to say with any confidence where the frilled shark is common and where it is absent. The distribution map in the scientific literature is a map of where humans have looked and occasionally seen or caught by accident. It is not a map of the animal. The animal lives in the space between the data points, in the vast dark stretches of canyon and slope that have never been visited by a camera or a net or a human eye, holding itself in cold suspension in water that has been still and dark and cold since long before the instruments that might detect it were built. And the water continues, 800 meters, 10 degrees Celsius, 60 atmospheres of pressure, and the slow chemical language of the deep, calcium and silica, and dissolved oxygen, and the electrical signatures of living tissue drifting on the current. The canyon wall falls away below and rises again above. A current moves along the rock face with the steady, unhurried persistence of deep water following pressure gradients that have been in place for longer than the canyon itself. Somewhere in that current, in the dark, a pale, elongated form rests in neutral suspension, its sensory organs registering the world in terms the surface has no words for, doing what its kind has done along these slopes since the chalk was still soft at the bottom of a warm Cretaceous sea. Above, on the surface of Saruga Bay, the gray morning continues. A fishing boat crosses the bay in the direction of the outer shelf. The wake it leaves spreads outward and dissipates into the ordinary chop. The water below it has no memory of the crossing. 800 meters down, nothing changes. The cold is the cold it has always been. The dark is the dark it will remain. The frilled shark drifts in the current along the canyon wall, suspended in the ancient water, unhurried, ancient itself, belonging entirely to the stillness it inhabits. At 700 meters below the surface of the ocean, the water is perfectly still. The temperature holds near 10 degrees Celsius. It is held there within a degree or two of that same value for longer than any human structure has stood on land. There is no light, not the faint blue dimness of 100 meters down, not the gray-green shadow of 200, nothing at all, a darkness so complete and so evenly distributed in every direction that the word darkness barely covers it. The pressure at this depth is more than 70 times the pressure of the air above the surface of the sea, and it presses inward from all sides simultaneously, steady and total and without interruption. In this darkness, in this cold, In this perfectly distributed pressure, there is a frilled shark. It is not moving. Its body hangs suspended in the water column, held there not by the motion of its fins, not by any muscular effort at all, but by something far more economical. Deep inside the body cavity, occupying a substantial portion of the animal's interior, the liver lies pale and dense, filled with a lipid called squalene. Squalene is lighter than water. Not by much, a small margin, a fraction of a gram per milliliter, but in a medium where every fraction counts, that slight reduction in density is enough. The liver acts as a float, counteracting the weight of the shark's cartilaginous skeleton and dense muscle tissue, distributing its buoyancy through the body with the same quiet efficiency as a sealed vessel of trapped air. The shark does not rise, it does not sink. It remains precisely where it is, at the depth it chose, in the dark it knows, without any expenditure of energy at all. This is how the frilled shark waits. It may have been waiting for hours before this moment. It may wait for hours more. In a body whose metabolism runs at the slow, cold-governed pace of a deep-sea organism at 10 degrees Celsius, the distinction between resting and hunting is nearly invisible from the outside. The shark drifts at the edge of a submarine canyon wall or against the face of the continental slope, its body oriented loosely in the current, its lateral line canals receiving the faint pressure signature of everything moving anywhere within several meters of its position. The water carries information. At this depth, in this cold, there is a great deal of information in the water, and very little urgency in receiving it. The shark receives it all. A squid is moving through the water column somewhere above, and to one side. It is not visible, nothing is visible, but the faint rhythmic displacement it leaves in the water as it jets forward, the pattern of micropressures expanding outward from its body at the speed of sound in water, arrives at the frilled shark's lateral line as a coherent signal. The shark processes this signal in whatever slow, cold way it processes signals in the dark. It does not turn toward the squid. Not yet. The squid is still some distance away, moving on its own trajectory, uncertain of its course. The shark holds still and waits, and the squalene in its liver holds it in place while it does. There are other sensory channels open in the dark alongside the lateral line. The ampullae of Lorenzini, small fluid-filled pores distributed across the head and snout, detect the faint electrical fields generated by the muscular activity of living animals. Every creature in the sea that moves its muscles creates a small electrical field. The squid, jetting upward through the dark water with the rapid contraction of its mantle, generates a field that expands outward through the seawater in all directions, faint and brief but real. At close range, within a meter or two, the frilled shark's ampullae can feel it. The two systems together, the pressure wave detection of the lateral line and the electrical sensitivity of the ampullae, form a net of information cast continuously into the dark around the shark's body, gathering everything the darkness does not show. The squid is closer now. In the cold water above the canyon, the squid moves without any awareness of the pale form below it. It is perhaps 40 centimeters long, its arms trailing as it hangs neutrally buoyant between one jet and the next, its own photoreceptors registering nothing but total darkness in every direction. It belongs to one of the many deep-sea squid species that spend their lives in the mesopelagic zone, ascending toward shallower water at night to feed on smaller animals, descending again before dawn. It has likely been moving for hours through this darkness, following gradients of chemical trace and pressure signal, covering ground that would take a human diver a very long time to cross. At about this point, something changes in the frilled shark's posture. The change is small and very slow. The body, which has been hanging in a loose, roughly horizontal position, begins to shift. The vertebral column, longer and more flexible than that of almost any other shark, begins a gradual lateral curve. The head tilts slightly. The pectoral fins, small and reduced, adjust their angle almost imperceptibly. From a distance, in a light that does not exist here, the motion might look like nothing at all, a gentle sway in a current, but what is happening is a coiling. The frilled shark is drawing its body into a slow preparatory arc, loading the vertebral column the way a spring loads when compressed, building the potential for a rapid forward extension without yet releasing it. The squid continues its descent. The sharks of the open midwater, the fast pelagic hunters, work differently. They pursue. Their locomotion is built for sustained speed, for closing distance across open water, for the energetic expenditure of a chase. The frilled shark's body is built for none of these things. Its single small dorsal fin sits far back near the tail, offering little control for high-speed maneuvering. Its pectoral fins are reduced, its caudal fin undivided, its whole form more cylindrical than the compressed, lift-generating cross-section of a pelagic shark. Speed is not the point. Speed has never been the point. What the frilled shark has instead of speed is patience, squalene, and a jaw that can do something extraordinary. The squid comes within range. The strike, when it comes, is not slow. The vertebral column, which has been curving gradually for the past several minutes, releases. The body lunges forward in a single rapid extension, not the broad tail-driven acceleration of a pursuing shark, but a coiled strike more reminiscent of the movement of a constrictor than a fish. The head drives forward through the dark water, and then the jaw opens. The upper jaw of the frilled shark does not operate the way the jaws of most familiar animals operate. It is not fixed to the skull. It swings forward and downward, away from the brain case, on a set of loosely articulated cartilaginous struts, projecting out ahead of the snout in a wide arc, the mouth opening to a gape far larger than the shark's relatively slender head would suggest. This protrusibility is one of the oldest features of the elasmobranch jaw, the capacity to swing the upper jaw outward from the head, effectively extending the reach of the bite well beyond what a fixed jaw could achieve. In the frilled shark, this mechanism is developed to an exceptional degree. The gape can open wide enough to engulf prey roughly half the length of the shark's own body. The squid is taken, the multicusp teeth, approximately 300 of them distributed in rows across both jaws, each one bearing 3 fine, sharply inward curving cusps joined at the base, do not cut, they grip. The cusps angle backward toward the throat, so that any prey item attempting to back away from the bite drives itself further onto the points. The squid's body, compressed and held between rows of inward-angled tridents, has no avenue of escape. The jaw closes, and the upper jaw swings back into position against the brain case. The frilled shark, which was motionless 30 seconds ago, is now in possession of a meal. The whole event occupied perhaps 2 seconds. The water around the canyon wall settles back into stillness. The frilled shark moves slowly away from the face of the slope, the squid compressing into the upper portion of the digestive tract, and finds again its depth, its temperature, its position in the dark. The squalene in the liver distributes the animal's weight evenly through the surrounding water. The lateral line resumes its listening. The ampullae remain open. The shark is, to all external appearances, resting again, though something new is now occurring deep inside its body, in the slow chemical dark of its digestive system, and it will continue for a very long time. The stomach of the frilled shark is not a quick organ. Nothing in the frilled shark is quick, not in the sense that warmth and activity make quick. The water outside is 10 degrees Celsius, and the water inside, the fluid that bathes the stomach wall, that carries the digestive enzymes, that moves the products of digestion into the bloodstream, is very nearly the same temperature. Enzymatic reactions slow as temperature falls. The chemical processes that break down a squid's mantle tissue, that dissolve the chromatophores and the crystalline lens and the dense protein of the muscle bands, run at a fraction of the speed they would run in a warm-bodied animal. A warm water shark, digesting a comparable meal in water twice this temperature, would process it in hours. Here, at depth, in cold that has not varied for geological epochs, the same process may take days. There is something to dwell on in this. The frilled shark ate, and now it carries its meal through the dark water, while that meal slowly, steadily, over the course of several days, transforms into the energy and tissue the animal will use to hunt again. Each hunting event in this calculation must sustain the shark not just for the hours until the next one, but potentially for much longer, for days, or for the time it takes the cold deep water to yield up whatever it will yield. The meal is not a quick transaction. It is a slow transfer, spread across time the way heat spreads through a cold stone, evenly, without hurry, not arriving all at once. Helping this transfer is a structure that belongs to a very old branch of vertebrate design, descending through the body cavity of the frilled shark, occupying the region of the digestive tract that in a mammal would be called the small intestine, is a spiral valve. It is not a tube. It is a helix, a corkscrew of soft tissue wound down through the interior of the intestinal wall, turning slowly inward on itself in a continuous spiral, its folded inner surface exposed to the contents of the gut at every point along its length. The spiral increases the total surface area of the intestinal lining enormously, compressing into the length of a short section of gut a mucosal surface that, if unrolled and flattened, would cover an area many times larger. In cold water, where each unit of digested material yields up its nutrients slowly, this expanded surface is not extravagance, it is necessity. The spiral valve is how an animal living at 10 degrees Celsius, eating infrequently, extracts everything it needs from what it has. The frilled shark drifts along the canyon wall with this slow spiral working inside it. The squid that was alive 20 minutes ago is now beginning its chemical dissolution in the stomach above the valve. The mantle is softening. The dense muscular tissue that powered the squid's jet is loosening into its component proteins, which the stomach's acid environment is already beginning to cleave. In a day, or in 2 days, the partially digested mass will pass into the spiral valve and begin the long descent through its folded passage. The nutrients, the amino acids from the mantle muscle, the lipids from the squid's own modest fat reserves, the minerals carried in its tissues, will be absorbed through the mucosal surface, one slow fraction at a time, entering the bloodstream and distributing through the shark's body to become, in time, muscle tissue and liver lipid, and the electroreceptive gel that fills the ampullary canals. Nothing is wasted. Nothing is rushed. In the dark, at this temperature, there is no mechanism for either. Some hours later, the interval impossible to specify, governed by the cold and the chemical state of the digestive tract, rather than by any clock, the frilled shark is still moving slowly along the continental slope. Its position has shifted, perhaps a few hundred meters from where the strike occurred. It is still at depth, still in the dark, still at the temperature that has defined this environment for longer than the shark lineage has existed in its current form. The lateral line is still listening. The squalene is still floating. Stomach content studies conducted on frilled shark specimens recovered as incidental bycatch from deep-sea trawls across the Atlantic, Pacific, and Indian Oceans have given a partial picture of what this animal eats across the broader pattern of its life. Squid dominate. The cephalopods found in frilled shark stomachs include some of the deep-sea species common in the mesopelagic zone, soft-bodied, fast-moving, energetically dense, and the consistency of their appearance across specimens from widely separated ocean basins suggests this is not opportunism, but something closer to a preferred prey type, the animal for which the frilled shark's particular combination of patience, squalene buoyancy, coiled strike, and protrusible jaw is most effectively calibrated. Deep-sea bony fishes appear as well. Lanternfishes, small, schooling, mesopelagic animals that rise toward the surface at night and descend again before dawn in one of the largest daily migrations of biomass on Earth, have been found in frilled shark stomachs. Rat tails, which move through the water above the ocean floor in the deep benthopelagic zone, appear in the record too. Occasionally, the contents include the remains of smaller elasmobranchs, other sharks or rays or their relatives, taken whole or in large pieces. The picture this assembles is one of broad, patient opportunism within a general preference. The frilled shark eats what the mesopelagic zone offers, weighted toward squid, taking whatever presents itself at the right range and in the right posture to be struck. What determines the right posture is partly a question of the prey's trajectory and proximity, and partly a question of the frilled shark's own position in the water column. Because the squalene-filled liver maintains neutral buoyancy at a specific depth, and because adjusting that depth requires either metabolic effort or behavioral movement, the frilled shark likely has a preferred operating layer, a band of depth where its buoyancy is most effective, where the water temperature best matches its enzymatic chemistry, where the density of suitable prey is highest, and the mesopelagic zone between 500 and 1,000 meters encompasses a great deal of biological activity, the daily migration of lanternfish, the vertical movement of squid between feeding and resting depths, the passage of larger animals moving through the water column in both directions. A predator stationed in this zone, neutrally buoyant and sensory alert, intercepts traffic. It does not need to pursue. It needs only to position itself in the path of what passes, and to be ready when something passes close enough. This is the economic logic of the frilled shark's life, not the logic of speed or pursuit or dominance, but the logic of placement, patience, and efficient use of what arrives. In an environment where food is unpredictable, where the energy cost of chasing prey across open water may exceed the energy gained by catching it, the predator that moves least and waits longest comes out ahead. The squalene makes the waiting free. The coiled vertebral column makes the strike fast. The protrusible jaw makes the gape wide enough to take prey that would be too large for a fixed bite. The multicusp teeth make escape impossible once contact is made. Every element of the system supports every other element, and the whole system is conservative, consuming as little energy as possible at every stage, converting what energy it obtains into the slow, deep work of digestion and growth and eventual reproduction. For a long time, days perhaps, the spiral valve continues its work. The folded inner surface of the valve, covered in absorptive mucosa, receives the passing digestive contents and draws from them what the body needs. Amino acids cross the mucosal wall and enter the portal circulation. Lipids, emulsified by bile salts, diffuse across the lining and move toward the liver. The slow, continuous extraction is nothing like the rapid processing of a warm-bodied animal, nothing like the hurried absorption of a mammal whose high metabolic rate demands constant replenishment. This is patient extraction, cold water chemistry working over long hours to transfer the energy of a single squid into the living tissue of an animal that may not eat again for some time. The squalene in the liver, that same compound whose density differential holds the shark afloat, is itself a form of stored energy. Between successful hunts, the liver serves not only as a buoyancy organ, but as a reserve, a store of lipid that can be metabolized if the interval between meals extends long enough. Deep-sea animals that eat infrequently and unpredictably tend toward large livers for exactly this reason. The storage organ and the buoyancy organ are the same organ, a single elegant solution to two problems at once. The frilled shark carries its energy reserves in the very structure that holds it in the water column, so that the longer it survives between meals, the more slowly that reserve depletes, and in depleting, the buoyancy shifts subtly and the shark adjusts. Time moves slowly here. This is the defining fact of the frilled shark's world, the condition that underlies everything else about it. Temperature slows reaction rates. The Arrhenius equation, the mathematical relationship between temperature and the rate of chemical reactions, describes a world in which every 10-degree drop in temperature roughly halves the speed at which molecular processes unfold. At 10 degrees Celsius, an enzymatic reaction that would complete in 1 second at surface water temperatures of 20 degrees might take 4 seconds, or 10, or some intermediate value, depending on the specific enzyme and its substrate. Across an entire metabolism, the thousands of simultaneous reactions that constitute a living organism's internal chemistry, this slowing is not trivial. It is the difference between a shark that needs to eat every few days and one that might sustain itself on a meal per week or longer. It is the reason a gestation that would last months in a warm water species lasts years here. It is the reason the frilled shark grows slowly, matures slowly, and lives for a long time by the standards of comparable fish. Cold is not an obstacle in this world. Cold is the architecture. The frilled shark has spent the entirety of its evolutionary history in cold water. Its enzymes are built to work at 10 degrees Celsius, not in spite of that temperature, but because of their specific molecular structure, which holds its active shape at low temperatures rather than unfolding, as a warm water enzyme might in the cold. Its metabolic rate is calibrated to the available energy budget. Its digestion is calibrated to the chemical pace of the deep. Even its electroreceptive gel, the fluid inside the ampullae of Lorenzini, has physical properties shaped by the evolutionary pressure of cold, high-pressure water. The animal is not struggling against its environment. It is its environment, rendered in cartilage and squalene and trident teeth and a spiral fold of intestinal tissue descending slowly through the cold dark of the body cavity. The canyon wall passes by in the absolute darkness. The frilled shark moves along the slope at whatever speed requires the least expenditure of the energy still slowly arriving from the digesting squid. It is not searching exactly in the way a mammalian predator searches, with intention, with a mental image of prey, with a plan. It is moving through space in which its sensory systems are continuously active, registering what arrives. The lateral line receives every pressure displacement. The ampullae register every electrical field. The olfactory organs, sensitive to the diffuse chemical signals that spread through deep water from distant sources, parse the slow chemical gradient of the mesopelagic zone. All of these inputs arrive simultaneously, continuously, without requiring attention in any sense a waking mind would recognize. The shark passes along the edge of the canyon, and the canyon edge does not notice. The water displaces around the body and falls back into place. The pressure signature of the shark's own movement spreads outward in all directions and fades within a few body lengths. In the total darkness and the total silence of 700 meters, the passage of this animal leaves almost no trace. Hours later, perhaps, or the next day, or the day after that, the cold makes the intervals uncertain in any human accounting. The digestive process has progressed far enough that the shark's energy reserves are no longer depleting. The absorbed nutrients from the squid are being distributed to the tissues that need them. The liver is receiving lipids. The muscles, which contracted briefly during the strike and have since been almost entirely still, are being maintained. The sensory systems, which run continuously and cannot be switched off, are drawing their small metabolic cost from the pool of absorbed energy. The shark is sustaining itself. It is doing this on the energy of one meal, spread across days of slow chemistry, while it waits for the next one. This is not deprivation. This is the design. The mesopelagic zone at night is different from the mesopelagic zone at day, even though at depth, the difference in light is imperceptible. The biological difference is real. As surface darkness falls, the daily migrators begin their ascent, the lanternfishes rising from their resting depths toward the surface layer, the squid following the vertical gradient of prey, the amphipods and euphasids ascending in vast and diffuse clouds that extend upward through hundreds of meters of water, and some portion of the mesopelagic zone, the layer between 500 and 1,000 meters, empties slightly as its migrating residents rise. Then, before dawn, the descent begins again and the zone refills. The frilled shark, which cannot see any of this in the dark, detects it through pressure, through chemistry, through electrical signal. The ascending column of lanternfish produces a diffuse disturbance in the lateral line, many small animals moving in the same direction, their individual pressure signatures overlapping into a general gradient. Whether the frilled shark tracks this gradient upward to follow the migrating schools, or whether it remains at depth and intercepts the descending column on the return journey, is not known with any certainty. The behavioral ecology of the frilled shark in the deep ocean remains largely unconstructed, built from inference rather than observation, from the contents of stomachs rather than the record of behavior. What the animal actually does between one confirmed sighting and the next is as dark as the water it inhabits. What is known is the output of the system. The shark persists. It eats, it digests, it waits, it eats again. Across years of this pattern, it grows slowly toward reproductive maturity. When it has grown enough, it will reproduce, and the cycle will extend itself into another generation. The economy of the system is self-sustaining, in the same way that the deep ocean itself is self-sustaining, cold and stable and enormously patient, running at a pace that the surface world barely registers. Somewhere along the canyon wall, in the dark, another squid is moving. This one is larger than the last, perhaps 50 centimeters, a deep-water species with arms adapted for catching smaller prey in the mesopelagic. It moves on an erratic path, jetting forward and pausing, hanging in the water column between pulses of its mantle, trailing chemical trace in the water that diffuses slowly outward in a gradient. The frilled shark, now several hours past the last meal and operating well within its energy reserves, is positioned below and slightly to one side of the squid's path. The lateral line registers the pressure pattern of the squid's mantle contractions. The ampullae, as the squid comes within range, begin to detect the faint electrical field of its muscular activity. The olfactory input carries a trace of the chemical compounds released by the squid's metabolic activity into the surrounding water. The three channels arrive simultaneously at whatever processing center integrates them in the frilled shark's brain, and something in that integration shifts the shark's posture from passive reception toward the slow preparatory curve. The vertebral column begins to flex. The head turns fractionally toward the squid's position. The pectoral fins adjust their angle. The body draws itself into the same gradual coiling that preceded the last strike, and the one before that, and every strike in the life of this animal, and every strike in the lives of its ancestors, stretching back across the geological record to a time before the Cretaceous chalk was deposited, before the sea that covered the land that is now England had fully formed, before most of the organisms alive on Earth today had yet appeared. The coil tightens, the squid descends, the distance closes. In the body cavity, the spiral valve continues its slow work, the previous meal still moving through its folded passage, its chemical contents still being drawn across the mucosal surface, one fraction at a time, the whole process still hours from completion. The new meal, when it arrives, will queue behind this one in the patient sequence of the gut, waiting its turn in the cold, dark chemistry of an animal that treats every calorie as something to be fully accounted for, slowly and without waste. The squid comes within range. The body releases. The jaw swings forward. And in the dark, at 700 meters, in water that has held its temperature and its chemistry and its darkness without significant variation for longer than words usefully describe, the frilled shark eats again. The water settles. The pressure waves from the strike spread outward in all directions and diminish within a few body lengths to nothing. The canyon wall stands as it has stood. The cold flows upward along the slope from the deeper water below, carrying minerals and the chemical traces of distant biological activity. The lateral line of the frilled shark, its second meal now secured, resumes its quiet reception of the dark. This is how the hours pass here. This is how the days pass. One meal, then the long interval of digestion, then another meal, then another interval, each one a small closed loop of patience and efficiency and cold water chemistry, each one adding incrementally to the slow accrual of the animal's life. The system does not hurry. It cannot hurry. The water will not permit it, and the animal was never built to try. What moves through the spiral valve in the cold is not just the digested tissue of a squid from the mesopelagic zone of a submarine canyon in the dark. It is the input to a biological machine of extraordinary age, moving through time at the pace of cold water, converting the energy of the deep ocean into the continued existence of one of the oldest body plans still operating on this planet. The shark eats, and the energy of the squid becomes the shark, and the shark waits in the dark, and the deep ocean continues around it, and the cold holds everything in place. Somewhere above, many hundreds of meters above, the surface of the sea reflects whatever light the sky is offering today, gray or silver, or the flat blue of a clear midday that means nothing at all at this depth. Ships pass. Weather moves across the ocean in long, slow patterns that reach down as far as the thermocline and no further. Below the thermocline, the world runs at its own pace, undisturbed, and the frilled shark hangs in the middle of it, with a second meal beginning its slow chemical transformation in the dark of the body cavity. The spiral valve turns, the squalene floats, the lateral line listens. Time passes, in the way time passes at the bottom of a cold, dark world, not in the sharp increments of clocks and tides, but in the slow, even currency of digestion and waiting, and the faint signals arriving from the water, one after another, steady and unhurried, deep into the dark. Inside the body of a female frilled shark, somewhere along the dark face of a continental slope, in water that holds steady near 10 degrees Celsius, and has held there without interruption for longer than any record exists to measure, something very small is growing. It has been growing for months already. It will continue growing for years more. The cold slows everything, every division of cells, every folding of tissue, every incremental step of development, so that what, in a warmer animal, might take weeks, stretches here into seasons, and what might take seasons stretches into something approaching the span of a human childhood. There is no urgency in it. There is only the slow, quiet accumulation of a life taking shape in the dark. The embryo is a few centimeters long. Its body is already recognizably shark-shaped, the elongated cylinder, the small fins beginning to form at their posteriorly placed stations, the head rounded and blunt at the snout. Along the sides of the throat, the gill arches are already faintly visible, already faintly fringed at their margins with the earliest suggestion of the frilled collar that will one day give this animal its name. Attached beneath the embryo's body, still large relative to the whole, is the yolk sac, pale gold and dense with the concentrated energy of lipid and protein that will nourish this developing animal across a gestation measured not in months but in years. It diminishes slowly. The embryo grows slowly. Everything in this dark, cold, pressurized place runs on a clock set far slower than the one that governs the surface world. The gestation of the frilled shark is estimated at approximately 3.5 years. That figure, when encountered plainly, asks to be held for a moment before moving past it. 3.5 years. A human pregnancy lasts 9 months. An elephant, which carries the longest gestation of any land animal, gestates for nearly 2 years. The frilled shark, in its cold, deep uterine space, surpasses both. It may carry the longest gestation of any vertebrate animal on Earth, a consequence not of unusual developmental complexity, but of simple thermal physics, the way low temperature slows every biochemical reaction, the way the dark cold of the deep ocean stretches time like a material that can be pulled thin without breaking. The reason lies in chemistry. Every reaction that builds a body, every enzyme binding its substrate, every strand of nucleic acid copied and checked, every membrane assembled from its lipid components runs faster when warm and slower when cold. In the shallow, sun-warmed waters where many sharks reproduce, these reactions proceed at a pace compatible with gestations of months. At 600 meters, in water near 10 degrees Celsius, those same reactions run at a fraction of their surface speed. The embryo develops correctly. The sequence of events unfolds in the right order. Nothing is missing or abbreviated. It simply takes much, much longer. Time in the deep ocean is not compressed. It is extended, quietly, into a duration that feels to the surface world almost implausible. The mother carries her developing young internally. There is no placental connection between her body and theirs. Each embryo is enclosed within its own egg case, sustained entirely by its private yolk supply, and the mother's body provides only the stable thermal and physical environment of the uterus, the protection of her own body moving through the dark water. This mode of reproduction, internal fertilization, internal development, yolk-dependent nourishment, live birth of fully formed young, is called ovoviviparity, and it places the frilled shark in a reproductive tradition shared by many elasmobranch, a tradition that emphasizes the quality of individual offspring over their quantity. 6 to 12 pups per litter, each one nourished across years, each one born already complete. What a newborn frilled shark looks like at the moment of its entry into the open ocean is something worth dwelling on. It arrives at somewhere between 40 and 60 centimeters in length, a slender, pale cylinder already bearing the full complement of adult characteristics. The trident-tipped teeth are in place, functional, seated in their rows along the jaws. The lateral line canals run along the flanks, their fluid-filled chambers already tuned to the pressure disturbances of passing prey. The ampullae of Lorenzini cluster around the snout, each one already capable of detecting the faint electrical fields that living bodies generate in salt water. There is no larval stage. There is no period of incompletion, no transitional form that must be sheltered through a vulnerable phase before the adult tools are ready. The frilled shark pup enters the world as a fully equipped predator, in miniature, needing nothing from its mother from the moment of birth. That independence is total and immediate. The mother provides no guidance, no territory, no shared food. What the pup has, it was given across 3.5 years of slow construction inside the cold dark of the uterus, and everything else it must find on its own. This is the bet the frilled shark's life history places on each individual. Not many bets, 6 to 12 per litter, across a gestation that spans years, following a maturation period that may itself take more than a decade, but each bet made with extraordinary care and thoroughness, each pup sent into the deep ocean as complete an animal as the long cold gestation could produce. There is a particular kind of patience in this. It is not the patience of waiting. It is the patience built into the design of a life, the patience of a species that trusts time to be sufficient. A female frilled shark reaches sexual maturity somewhere between 135 and 150 centimeters in body length. Males mature somewhat earlier at 100 to 120 centimeters. The rate at which the frilled shark grows toward these lengths is not precisely known. Direct measurement of living animals across time requires encounters that are themselves extraordinarily rare, but the evidence from related deep-sea elasmobranch species and from the overall pattern of the frilled shark's biology suggests that the decade mark may pass before reproductive maturity is reached, perhaps longer. The cold slows growth as it slows everything else. A frilled shark that has lived for 10 years may still be years away from its first reproduction. The investment the species places in each individual is not only measured in the length of gestation, but in the years that precede gestation, in the slow accumulation of body size and internal readiness that must happen before the animal can contribute to the next generation at all. This is what biologists call a case-selected life history strategy. The letter refers to the carrying capacity of an environment, the theoretical maximum population an ecosystem can sustain, and the strategy describes an approach to reproduction that prioritizes individual quality over numerical output. Few young, heavily invested in, born large and capable, slow to mature, long-lived, occupying stable ecological niches where their particular specializations are consistently rewarded. The frilled shark fits this pattern precisely. It occupies a physical environment of extraordinary stability. The temperatures, the pressures, the salinity values have changed very little across the timescales relevant to the species' evolution, and its life history reflects that stability. It is an animal built for a world that does not change much, and in such a world, the strategy works. The slow and the heavy investment, and the careful production of a small number of well-made young is a perfectly adequate approach to continuation. It has sustained this lineage across vast stretches of geological time. The female, having gestated her litter across those 3.5 years, gives birth somewhere in the dark along the continental slope. No human observer has ever witnessed this event. No camera has captured it. No specimen has been recovered in the act. The inference that it happens, that it must happen, and that it happens in the kind of environment the species inhabits, comes from life history data, from the examination of pregnant females recovered incidentally from trawl nets, from the presence of near-term embryos measured and documented in laboratory settings. Somewhere along these dark, steep walls of rock and sediment, in water that has never been reached by sunlight, the transfer occurs. The pups enter the ocean column independently and immediately, and whatever brief adjacency of mother and offspring exists in that moment leaves no record and has left no witness. It is one of the most ordinary things this species does, and one of the most completely unobserved. There is a particular quality to scientific knowledge about the frilled shark's reproduction that deserves its own attention. For the developmental facts, the ovoviviparity, the yolk-dependent nourishment, the litter sizes, the birth lengths, there is real data recovered from real specimens, cross-checked across multiple populations and ocean basins. These are solid facts, grounded in physical evidence. For other parameters, survival rates, natural mortality, population size, the actual duration of the growth period to maturity, the home range of an individual across its lifetime, there is almost nothing. The number of frilled sharks that exist in any given ocean is not known. Whether the populations in different ocean basins are connected or isolated is not known. Whether the species is increasing in number, decreasing, or holding approximately stable is not known. The data required to answer these questions does not exist, because the frilled shark lives in a place and in a way that has made systematic study nearly impossible. What is known about the source of most frilled shark specimens says something both practical and sobering about this gap. The majority of individuals ever examined by scientists arrived not through directed survey or deliberate research, but as bycatch, animals recovered incidentally from the nets of deep-sea commercial trawl fisheries, targeting other species at depth. The frilled shark was not what the trawl was after. The frilled shark was simply present in the depth range the trawl swept through, and was collected alongside the intended catch, and was sometimes preserved and delivered to researchers, and was sometimes not. The actual number of frilled sharks taken as bycatch across the full scope of deep-sea trawl activity worldwide, across all fishing nations, all depth ranges, all decades of operation, is not recorded in any systematic way. Bycatch reporting from deep-sea fisheries has historically been inconsistent and incomplete. What reaches the scientific record is a fraction of what is actually removed. This creates a peculiar situation. The frilled shark's official conservation status, as assessed by the International Union for Conservation of Nature, is least concern, a designation that places it among the large proportion of species judged not to be at immediate risk of extinction. The least concern designation is not a declaration of flourishing, it is a declaration of insufficiency. Insufficient evidence to classify the species as threatened, insufficient data to conclude that its numbers are in decline, insufficient information to support a higher risk listing. The annotation that accompanies the assessment is quiet and specific. It acknowledges that data are lacking. It notes that actual bycatch levels are unknown. It identifies the species' slow reproductive rate as a factor that would make population recovery from significant mortality slow if such mortality were occurring. The designation is the best available conclusion from the available evidence, and the available evidence has gaps as wide as the deep ocean is dark. Those gaps are not comfortable to rest in, but they are important to name honestly. The frilled shark's situation is not a known catastrophe. It is an unknown, and unknowns for animals with this particular combination of biological characteristics, the slow growth, the late maturity, the multi-year gestation, the small litters, the deep and inaccessible habitat, carry a weight that the bare designation of least concern does not fully communicate. An animal that takes a decade or more to mature, that gestates its young across 3.5 years, that produces 6 to 12 pups per litter, cannot recover quickly from population-level disruption. If bycatch mortality were significant and sustained, the demographic arithmetic would work slowly and in only one direction. The species would not crash suddenly. It would diminish gradually, at a pace too slow to detect against the background noise of an inadequate monitoring system, until the diminishment had already run well ahead of any response. This is not stated to generate alarm. The frilled shark has been present in the ocean since long before the current geological period. It survived the end Cretaceous extinction event that removed the non-avian dinosaurs and reshaped marine ecosystems across the planet. It persisted through the oceanographic changes of the Paleogene and the cooling of the Neogene and the climatic oscillations of the Pleistocene. It has demonstrated a capacity for survival across timescales that dwarf the brief period of industrial deep-sea fishing. Its deep-water habitat, while not entirely shielded from human activity, is considerably less altered than coastal and shallow reef systems. The picture is not one of imminent loss. It is one of quiet uncertainty, held alongside the species' demonstrated capacity for persistence. What the frilled shark risks by living slowly in an accelerating world is not extinction in any dramatic or proximate sense. What it risks is the slow erosion of margin, the narrowing of the buffer between its actual population size and the threshold below which recovery becomes self-limiting. The margin may still be wide, the buffer may still be large. The science simply cannot say with confidence how wide or how large, because the measuring instruments, the surveys, the monitoring programs, the systematic bycatch records have not yet been built for this animal in this environment. The frilled shark exists for the purposes of conservation biology in something like the condition it exists in for human eyes more generally, present, real, continuing, but almost entirely beyond the reach of direct observation. A pup, born somewhere along the cold, dark slope, enters the water column at 45 centimeters of pale, perfectly formed length. Its yolk reserves are gone. Its teeth are ready. The lateral line responds to the movement of water around it, to the faint pressure signatures of things alive and moving nearby. The ampullae at the snout can feel the electric whisper of a small body's muscle contractions at distances of several body lengths. The animal is not yet an adult. It has years of growth ahead before it reaches the size of sexual maturity, and more years after that before its physiology will be ready to reproduce. But in the immediate sense, it needs no help. It drifts away from the site of its birth, if drift is even the right word for the deliberate, slow, undulating motion of a small frilled shark moving through dark water, and it begins the long, unhurried business of living. The cold water holds at 10 degrees. The pressure is enormous and constant. There is no light at all, not a photon filtered down from the surface, not a trace of dawn or season or the movement of the sun across the sky far above. The pup orients by the feel of water against its body, by the electrical geometry of its immediate environment, by the vibrations carried through the medium it swims in. It is entirely at home here. It was built for exactly this: the dark, the cold, The pressure, the slow time, everything about its body reflects an adaptation to these precise conditions, and the conditions themselves have been consistent for so long that there has been no selection pressure to change the adaptation. The pup that enters this water is essentially the same animal that entered it 100,000 pup generations ago. The dark and the cold and the pressure have preserved the design as surely as they preserve everything else that lives within them. Growth is gradual. Year by year, the pup that was 45 centimeters at birth adds length slowly, fattening the oil reserves in its liver as its body grows large enough to sustain the longer periods of stillness that more successful ambush requires. A juvenile frilled shark is probably a less efficient predator than an adult, smaller, with a narrower gape, a less extensive lateral line, a liver not yet large enough to provide full neutral buoyancy across extended motionless waiting. It hunts and sometimes misses and goes hungry for stretches that in a warm-blooded animal would constitute a crisis, and here constitute a normal interval between meals. The spiral valve intestine extracts what it can from what it receives. The liver's squalene reserves buffer against lean periods, releasing energy slowly as the animal holds itself in suspension in the dark. The first year passes. The second, the body lengthens. The liver grows proportionally within the body cavity. The gape widens. The lateral line deepens in sensitivity as more receptor units develop along its length. The animal that began as a 45 centimeter pup is becoming one cold, slow year at a time, the sleek and patient predator that its lineage has been producing across geological spans of time. There is no awareness of this in the animal. There is no sense of progress toward a destination. There is only the water and the darkness and the slow accumulation of size and capacity, and the occasional meal caught and swallowed and digested across days of cold water chemistry. Time in the deep ocean is not something that is used. It is simply something that passes, vast and quiet and indifferent, and the animals that live within it endure. At some point, perhaps at 12 years of age, perhaps at 15, the precise threshold unknown, a female frilled shark reaches the length at which internal physiological changes make reproduction possible. The liver is now large and fully laden with squalene. The body is at or near its adult length. The lateral line and the electroreceptive system have reached their full development, and in the darkness of the deep water, in conditions that have not changed measurably from the conditions the animal was born into, fertilization occurs. The embryos begin to develop. The yolk sacs form around them. The slow clock of cold water gestation begins to tick. 3.5 years from that beginning, somewhere along the dark face of the slope, in water at 10 degrees Celsius and under pressures the surface world will never feel, the cycle completes itself again. 6 pups, perhaps, or 8, or 12, each one 45 centimeters, of pale, perfectly formed frilled shark, enter the open water independently and immediately. They carry no knowledge of what they came from. They need none. Everything they require was built into them across the years of their making, in the dark and the cold, in the gradual diminishment of a golden yolk sac pressed against a forming body that was, across all those quiet years, becoming itself. The ocean holds them, the same cold water that has held their lineage for tens of millions of years, the same darkness, the same pressure, the same stability that slows time and preserves forms and keeps the world at 600 meters, almost unchanged across geological spans. The frilled shark does not know this. It does not need to. The knowing is distributed across the whole of the lineage, inscribed in the biochemistry and the anatomy and the reproductive schedule of every individual, and it does not require a mind to hold it. It simply persists, the way cold water persists, the way darkness persists, the way the deep ocean persists below the surface of all human understanding, slow and vast and largely silent, continuing in its ancient way. A frilled shark at rest in the water column at 700 meters is very nearly invisible to any instrument or eye that tries to find it there. It makes no sound. It displaces the water around it so gently when it moves that the pressure wave is smaller than the background noise of the deep ocean's own slow currents. Its pale body in the total darkness reflects no light because there is no light to reflect. The lateral line detects the world around it. Nothing detects it in return. It is present and invisible in the way that very old things are often invisible, not hidden exactly, but simply existing on a different register than the instruments designed to find them. What the frilled shark's existence asks of us, if asking is even the right frame, if a creature with no awareness of our existence can be said to ask anything, is something like the willingness to hold uncertainty without resolving it. Not to know how many there are, not to know whether the population is large or small, stable or shifting, not to know what a single individual's life looks like across its full span, how far it travels, how many meals it takes in a year, how long it lives before it dies of age or injury or swallowed by something larger or entangled in a net it never saw coming. To hold all of that unknowing gently, without the discomfort that unknowing usually generates, and to recognize that the animal continues whether or not the knowledge exists. The frilled shark does not require understanding to persist. It requires only the cold and the dark and the slow, deep time that has always sustained it. The continental slope where a female carries her litter tonight, if tonight is even a meaningful word at 600 meters, where no day has ever broken, is unremarkable by human standards. Rock and sediment, the slow movement of cold water along the canyon wall, the occasional passage of something living, detected and ignored or detected and pursued, the arithmetic of predation playing out in darkness with no witness. The embryos inside the mother are perhaps a year into their development. The yolk sacs have diminished by roughly a third. The bodies are growing, cell by slow cell, building the teeth and the lateral line canals and the squalene-laden liver that will one day hold another frilled shark suspended in the dark water of its own deep world. There is no hurry. There has never been any hurry here. The depth and the cold and the pressure that make this place so inhospitable to most life are precisely the conditions that have sheltered this lineage from the forces that alter and eliminate and reshape. The stillness is the shelter. The slowness is the safety. The darkness, which seems to the surface world like deprivation, is what has allowed this form to remain itself across spans of time that make all of recorded human history feel like a single indrawn breath. The embryo turns slowly in the dark of the uterus. The yolk sac gives up its stores, molecule by molecule, across the long, cold gestation. Outside the mother's body, the canyon wall descends into depths she will never visit, into pressures even her cartilaginous frame could not sustain. Above her, 600 meters of black water rise toward a surface she has never seen and will never see, where the sun moves through its cycles entirely without consequence to anything that happens in her world. She drifts along the slope on the slow current, the squalene in her liver holding her at neutral depth without effort, the lateral line reading the water ahead of her for the electrical and pressure signatures of the things she feeds on. The lives inside her body continue their slow becoming. The cold holds steady. The dark holds steady. The water moves in its ancient patterns along the face of the slope, as it has moved for longer than the species has existed, as it will continue to move long after this particular animal and all her young have dissolved back into the medium that made them. Something in the mathematics of this, the 3.5 years of gestation, the decade or more to maturity, the small litters, the cold, slow chemistry of everything, is the arithmetic of a species that trusts the world to remain consistent. Not because it has chosen to trust, but because it was built in an environment where consistency has been the rule for so long that building for anything else would have been unnecessary. The frilled shark is an answer to a question the deep ocean has been asking for a very long time, and the question is simply, what shape does life take when the world does not change? The answer is this: a pale elongated form drifting in total darkness at 10 degrees Celsius, a yolk sac diminishing across years, a pup entering the water column already complete, a lineage continuing in the dark, unhurried and unseen, for as long as the dark and the cold and the deep, slow pressure continue to hold. The water at 600 meters tonight is the same temperature it was 1,000 years ago. It is the same temperature it will likely be 1,000 years from now. The frilled shark moving along the canyon wall is built of atoms that were once part of other animals, other bodies, other slow, deep lives that dissolved and were taken up again into new forms in the endless cycling of matter through the ocean's depths. The atoms that make her liver squalene were once part of some other creature's body, something simpler, something older, something that lived and died in the same cold, dark water in an era before any human eye existed to observe it. The atoms will be part of her litter's bodies after her, and part of something else's body after that, passed forward through the deep ocean's slow economy of matter across stretches of time that the surface world has no ready frame for. Nothing is lost, nothing is finished. The frilled shark's lineage is one long, quiet thread in the larger fabric of marine life, pulled through the needle of geological time again and again, holding its shape with a patience that belongs not to the animal, but to the conditions that produced it, and that have continued, uninterrupted, ever since. The embryo at the center of all this does not know it is ancient. It does not know it is rare. It does not know that the form it is slowly taking, the frilled collar, the trident teeth, the oil-filled liver, the lateral line running the length of its small flanks, is a form that the fossil record has preserved from 95 million years ago in the chalk of ancient shallow seas. It is simply becoming what it is, at the pace the cold allows, in the dark that is all it has ever known, and that is enough. It has always been enough. The slope continues downward into the abyss. The cold water moves in its slow currents along the canyon wall. The mother drifts in the darkness, the lives inside her turning slowly in the long gestation, the yolk sac giving its gold reserves up into the forming bodies of the young. Everything here is very old and very slow and very dark. Everything here continues.